Welcome to AI Frontiers, where we explore the cutting edge of artificial intelligence research. Today we're examining Intelligent Machines in Motion, a comprehensive analysis of 31 breakthrough papers in computer science robotics from December 2024. These revolutionary advances showcase AI-powered robotic systems that range from surgical precision to swarm intelligence, bridging artificial intelligence with physical world interaction in ways that represent the latest research from the cutting edge of embodied AI. Our journey through robotic intelligence today will take us through several fascinating territories. We'll explore how robots understand and execute natural language commands, transforming simple instructions into complex actions. We'll discover breakthrough methods for social navigation and human interaction that go far beyond basic obstacle avoidance. We'll examine scalable coordination algorithms for robot swarms that can manage hundreds of autonomous agents simultaneously. We'll unveil adaptive systems that learn from experience, building knowledge over time rather than starting fresh with each task. Throughout our exploration, we'll highlight 3 game-changing research papers that exemplify the current state of the art. Computer science robotics represents the intersection of artificial intelligence, computer science, and mechanical engineering, with a focus on autonomous systems that can perceive, reason, and act in complex environments. Think of it as the brain of modern automation, the intelligence that brings mechanical components to life. While traditional engineering builds the physical components like motors, gears, and sensors, computer science robotics provides the foundation for future human-robot collaboration. This field takes an inherently interdisciplinary approach, combining machine learning, computer vision, natural language processing, and control theory to create systems that can operate effectively in real-world environments. The first major research theme emerging from these papers focuses on embodied intelligence and natural language understanding. Korkemny and colleagues demonstrate hierarchical language planning systems that enable robots to understand intent, context, and the subtle nuances of human communication. This represents a fundamental shift from rigid programming to natural conversation, where robots can break complex household tasks into manageable subtasks. The research shows how robots can develop social context awareness in instruction interpretation, understanding not just what humans say, but what they mean in specific situations. This advancement moves us closer to robots that can truly collaborate with humans in intuitive ways. The second major research theme centers on social navigation, moving far beyond simple obstacle avoidance. Wang and colleagues pioneer multi-action social navigation approaches that enable context-aware movement, considering human comfort and social norms. This represents an evolution from basic point-to-point navigation to socially intelligent movement that understands concepts like right-of-way, emergency protocols, and anxiety reduction in human populations. The breakthrough here is achieving real-time processing for dynamic social environments, allowing robots to make appropriate social decisions in milliseconds. This research addresses the critical challenge of creating robots that don't just avoid bumping into people, but actively contribute to comfortable social spaces. The third and fourth research themes focus on memory systems and adaptive control mechanisms. Guo and colleagues develop scalable multi-robot coordination algorithms that represent a lifelong learning approach, replacing traditional stateless operation with systems that build knowledge over time. These advances include variable stiffness control that adapts to different tasks, learning from human demonstration through haptic feedback, and innovative gamification approaches for scaling robot training data. The significance here lies in creating robots that become more capable through experience, rather than requiring complete reprogramming for new situations. This represents a fundamental shift toward truly intelligent robotic systems. Several key breakthrough findings emerge across this research that are transforming the field of robotics. First, hierarchical planning approaches consistently outperform monolithic approaches for complex tasks, suggesting that organizing multiple specialized components intelligently is more effective than building single powerful systems. Second, vision language models successfully integrate into real-time robotic control systems without requiring extensive task-specific training. Third, Multi-robot coordination algorithms achieve unprecedented scalability while maintaining effective load balancing across robot teams. Fourth, bio-inspired swarms operate optimally near critical phase transitions between different collective behaviors. Finally, cross-modal learning enables knowledge transfer across different robotic systems, allowing robots to learn from human demonstrations captured through various sensing modalities. The methodological approaches shaping modern robotics research reveal several dominant strategies. Large language model integration provides high-level reasoning and planning capabilities, allowing robots to understand complex instructions and break them down into actionable steps. Vision language models process multimodal environmental information, enabling robots to understand both what they see and what they're told about their environment. Probabilistic planning methods handle uncertainty with formal guarantees, providing principled approaches to operating in unpredictable conditions. Hierarchical architectures enable specialized component coordination, allowing different parts of robotic systems to focus on their particular strengths. Learning from demonstration approaches leverage human expertise and intuition, scaling robot training through human-provided examples rather than extensive programming. The first seminal paper comes from Alexander Korkomny and colleagues with their work on HELP, the hierarchical embodied language planner for household tasks. This research represents a revolutionary approach to natural language instruction, interpretation in robotics. The system employs multiple specialized large language model agents, each handling different aspects of the planning process, from high-level task decomposition to specific skill mapping. The breakthrough lies in successful handling of ambiguous household task instructions, providing a template for integrating large language models into practical robotics applications. The research demonstrates effective decomposition of complex multi-step procedures, showing how robots can understand instructions like tidy up the living room and translate them into appropriate sequences of actions. The second seminal paper comes from Zishuo Wang and colleagues on MAction-SocialNav, which advances socially appropriate robot behavior through multi-action social navigation. This work addresses the inherent ambiguity in social navigation scenarios, where multiple appropriate responses often exist for any given situation. The system uses metacognitive prompting for explicit reasoning about social norms, generating multiple plausible actions that are evaluated against social criteria rather than just efficiency metrics. Operating at real-time processing speeds of over 1.5 frames per second, the system achieves significant improvements in social appropriateness metrics. This research represents a fundamental shift toward robots that understand and respect the subtle social dynamics governing human behavior. The third seminal paper comes from Zikun Guo and colleagues on structural induced exploration for multi-robot path planning, which presents a novel approach to the computationally challenging problem of multi-robot coordination. The research introduces structural induced exploration that leverages spatial task distribution to guide search processes more efficiently than traditional approaches. Using enhanced ant colony optimization with spatial bias initialization, the system achieves better load balancing among robots and significantly reduced mission completion time. This work demonstrates a crucial scalability breakthrough for large robot teams, solving the exponential complexity challenge that has traditionally limited multi-robot coordination to small groups of robots. Looking toward the future, several key directions are shaping the next frontier of robotics research. The integration of foundation models with real-world robotic constraints represents a major challenge, requiring researchers to bridge the gap between the impressive capabilities of large AI models and the practical limitations of physical systems. Development of more sophisticated uncertainty quantification methods will enable robots to operate more safely in unpredictable environments. Advancement in cross-modal learning and knowledge transfer will allow robots to leverage diverse types of training data more effectively. Exploration of bio-inspired collective intelligence principles promises new approaches to swarm robotics and distributed problem-solving. Enhancement of human-robot collaboration frameworks will enable more natural and effective partnerships between humans and robotic systems. In terms of our synthesis and review process, this analysis was created using advanced AI systems, including GPT and Anthropic Claude Sonnet 4, for content synthesis and analysis. Text-to-speech synthesis was generated using DeepGram technology to ensure high-quality audio output. Image generation was powered by OpenAI systems to create supporting visual content. All content underwent a human expert review process to ensure accuracy and completeness. However, we acknowledge that potential oversights may exist despite our thorough review process, and we encourage listeners to consult the original research papers for complete technical details. Thank you for joining us on AI Frontiers as we explore the fascinating world of computer science robotics. Subscribe to our YouTube channel for the latest AI research insights, with weekly deep dives into cutting-edge artificial intelligence research. Our expert analysis covers breakthrough papers and methodologies that are shaping the future of technology. Join thousands of others exploring the future of AI technology, making AI Frontiers your gateway to understanding tomorrow's intelligent systems. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.